So last week we think roughly finished the chapter 14, um, the Lagrange multipliers, right? So before we do some more practice and exercise on especially the Lagrange, and I think also we need to have some exercise on the maximum minimum value. First, I would like to ask, is everyone doing your quiz or not?
Yeah.
I think I just emailed you early morning because I just found out that there are, I think, a few students that are, I think, either the browser that they are using has more background files, which means that you know the word case, right? Casey, you know. You know the word? No. Okay. Sometimes when you are using your browser, if your browser too busy, means that it has much more memory that it should need. Then sometimes you need to go to tools and then you go clear Casey, and including whether you need to clear your history file, blah blah blah. And unfortunately, the platform that I'm using is I think sometimes it has a problem with this. Okay, so what I'm trying to say is a few students not really complete this submission because the system cannot read their answer. Okay. So I just sent an email. So please check your university email, your mail.ntsu.edu.tw. Check your email. If you are one of them, you can resubmit because I'm opening the quiz again just today. So try to just resubmit the answer so that I can easily look at your submissions. I think 6 to 7 students that fail the submissions. So how to deal with this Casey issue? You need to open first using your private browser, or if you are using Google Chrome, you can use the incognito mode because that will be not using your private Casey, your browser Casey. Then you will use another memory. Okay. I think that will be the best way. So you need to use your private browser or incognito. I'm not sure what the other one what it's called. I think if you're using Safari, you can use. I think it's called the private browser in Safari. Yeah. In Google, it's called the incognito. So you check your university email. If you're one of them, please do the submissions. Okay. We'll check again tonight. If there are still some students not getting the information, perhaps I cannot really grade the score. So please also make sure telling your friends if they miss out the class today. Okay. So only 7 students. Okay. So okay, let me give you more detail before we go to some practice on Lagrange. Or maybe we can go for practice. Okay, I think I just did. I told you before that if we have two constraints, which is constraint like another function g and h, which has some certain value, then we can limit this constraint and we can put into our formulation and it becomes two parameter. And this becomes 2 parameters. So the parameter lambda and parameter mu. Okay. This still is called Lagrange, but different value, a different type of value. I think we can just go to the exercise and see whether we have this two constraints type or not. Okay. So let's go to the exercise. But first, the exercise is this local maximum minimum. Maybe we could choose from this, maybe which one that we want to working on. Any idea which one we should work with from these 4 numbers? Maybe I couldn't complete by today all. Maybe one. Which one do you think? Any idea? Which one do you want to solve? The rest, I think you can solve. Try yourself by yourself. Exercise. How about 1, 2, 3, 4? 4. Okay, it's this one. Okay, let's try. So it says that you need to find local maximum, minimum, and saddle point if they have saddle points. So first is what we need to do. Okay, so first, let me just write the functions on the side. So we want to take this one, right? So let me write again the function. And then what we need to do, we need to take partial, okay, at least to find partial x and partial y. So if we take partial x, which means we are going to look at x in our derivatives, which means this part here, right? That's on x, y is this one. So x will be as a variable and y is as a constant. So we could write x squared plus 2 becomes 2x. So 2x, and then the other one is constant, so e y over 2. And then maybe try, I think on the sides I will write here, partial y. So we are going to derive the e. So e derive, it's become another e with the same value, but we derive the chain rule, y over 2, it becomes half, right? So it becomes e y over 2, and then x squared plus 2, and then we need to multiply with over 2. I think I missed out something. It's y. Sorry, we need to erase this part. But I think the first one's still okay, right? Yeah, I noticed that something strange, that it is maybe too simple. Should be this one, right? Okay, so x squared, y is a constant. Okay, I think this will be correct, the first one. So partial y, e, and then the other one will be 1, and then x squared. Or if you would like, maybe if you want to make it into this way, I think this is also okay, and then derive each one with respect to y. So this will get you to x squared. X squared plus 2 plus y, right, over 2. So 1 plus 0, okay. So we are going to have a product rule from this part. So if you like also, you can also look at this from 2 different functions like usual. Let's say this is u, v. You can say u prime v plus v prime u. And then we could derive each one of them. So we are going to focus on y. So u prime is just 1, and v is just e y over 2 plus v prime half y over 2, and then u is x squared plus y. Is it correct? Check. Half x squared, half y, half plus. Okay, this would be v x squared plus y. Or perhaps this one may be more easiest to see. Maybe like here. This is just checking is my answer correct. So this part becomes half e y over 2 and then x squared, and then plus, and then this is going to be product rule. So e y over 2 plus y e y over 2 over 2. Okay, I think this will be consistent. So we could write down and then make this conclusions here, right? Okay. Okay, I think okay. So anyway, you could do. Don't forget that every time you have a variable, multiply with another component that has variables. You need to do a product rule, right? Okay, just quick notes, and then don't forget that we need to have a partial xx, okay, which is the second partial for x. Or I forgot to mention that you could also take in the partial yy. Okay, this is to let you know whether it has a saddle point or not. Okay? If it's a less 0 or positive. Okay? So if it's negative or positive. So maybe let me write first the partial xx. This is going to be, so we derive again one more time. So 2 e y over 2, okay. And then partial yy. This will be a little bit crazy here. So but we just focus on e and y, right? E with part of y and y here. So half, so maybe half, let me focus that. So half e y over 2. And then this will be, need to be 4, right? 4 plus x squared plus y, right? So this will be 1 plus x squared, or 1 e and then we can write this. Yeah, it's very similar to from the previous one. Okay. And then also I think we could just state the critical points directly. Right? So from the partial x and partial y. So taking the partial x or partial y, taking it equal to 0. So it seems that, so when partial x is 0, it seems that the possible way that to make this happen is by taking, so let me write here that partial x is 2x ey over 2. So the possible way to make the partial x 0 is taking x 0, right? So it implies that the critical points probably this x equals 0. And then similarly, for partial y make it 0, this is when if you look here, if x is 0, as we mentioned before, so if this is 0, then the only way it could be collapsed into 0 is y need to be -2, right? So checking y, it should be -2. Oh, I forgot one more. The xy or yx. Just right here, maybe take xy. So it will be half 2x e y over 2, right? So this will be x e y over 2. It will be the same thing if you take x squared. This will be 2, and then constant will be 0. So 2x divided by 2 is x. So it goes also to be same as with this. Okay. So what can we do next is take d, right? So d is partial xx, partial yy minus partial xy and squared. And the point that we are going to evaluate is 0 and -2. So we take d at 0, -2. So we put into our all the equation that we need, partial xx. So when it's -2, so it's 2 over e, right? Partial yy, taking 0 and -2, so 1 over e, so this will be 1 over e, right, or 4e, and then 4 minus 2 is 2, so it's going to be half e, so 1 over 2 e. Okay. Oh, y here negative. Okay, yeah, correct. And then minus the xy is 0, right? 0. So 2, or we could say 1 over e squared. This is supposed to be a positive number, right? So we could say that d is positive. So this is positive. So what happened when d is positive? We need to check the so remember, okay, let me just write some notes. So if d is already negative, then we could definitely see that this will be saddle. Okay. But if d is positive, it means that we need to check the partial xx or partial yy. One of them, okay, it's okay. You could choose partial xx or partial yy. And if this is positive, this is negative. If negative, this is maximum. If positive, this is minimum. And then we check the partial, maybe xx, that is, I think, easy to follow. So partial xx is 2 e y over 2. So y is -2 over 2. So we see that this is 2 over e, which is another positive. So positive, right? So we see that at 0, -2, we say that the point is at local minimum. Sometimes when you choose the partial, the second derivative here, I think you could just choose which one is, I think, more easy to compute. Yeah, and I think partial x-axis, I think, easier than y1 here. Right? So I think you could just plug in the number into that partial x-axis, and then we get a value that is positive. Then we decide that this will be local minimum. But your questions within this range of questions, it's suggesting to take the graph. It means that perhaps you need to use some graph calculators, and I will try to use that. But let me just wait for a moment. You can try to write up the notes. So I think after this, one more question on Lagrange, and perhaps we look for the two constraint, and then we move to chapter 15. And if we still have more practice, I think I will prepare some sort of maybe 8 or 9 questions and give you some preparation, especially for a typical problem that might be appearing on at least some questions in the finals, in your finals. I will try to prepare that as well. I think maximum minimum will be on your finals for a little bit. Okay. It takes time because you may be not really familiar with the chain rule in partials, or maybe using the product rule that in the calculus 1. Now we use the same techniques, but we have two variables, and we need to remember which one that we derive it, because we derive it partially. We derive it partially to x or partially to y. So I think that also need to think about that. Okay. So I already prepared some graphs here in GeoGebra. I think not really showing. Wait. It's not showing. Yeah. Oh. Okay, good. But now I cannot. So it's where's my? Wait. Let me just show you this. Okay. So yeah, I think we try our best to get through. Is the equation correct? Square plus y. But you can do the same thing with your GeoGebra. Okay. So you could take that. So let me check again. Yeah, you could take that as well. Okay. Okay, back to the notes. Okay, now from this range of questions about Lagrange. Okay. I think number 62, because it has two constraints. As we mentioned, I need to find example for two constraints. So let's try number 62. So what's the basic idea in Lagrange? In Lagrange, basically what you need to do is you need to find the gradient factor, right? Both of the constraint and the f. Okay. So let's say the constraint, we name this as g, this is h, okay? So we need to find, first is taking the delta f, okay? Or the del f, or gradient f. That is, I think, quite simple. We just take partially everything inside and 6c, right? And then I think we could just describe right here that the constraint, so first is g and the second one is with the h. So we have, and we need to find the relation between these two, okay? And then somehow we can relate those two within this two parameter. So I think we could take directly here that this will be lambda and then multiply with the del g. I'm going to write first here to make it easier to see. Or perhaps directly write the del g here. Oh shoot, what happened? No. Oh. So del g is 111. H is 1, -1, 2, right? Okay, so we could see that 2x is equal lambda plus mu, right? And 4y is lambda minus mu. And then 6z is lambda plus 2 mu. Okay. And basically what we need to do, sometimes we need to solve using linear equations. Just eliminate, and then maybe looking for this and this, okay, lambda and mu. Or sometimes we can maybe just describe through some relation between this, and then perhaps we have some ratio that we can relate from this two. Okay, so sometimes we can do that. Okay, and then we also remember that we have a constraint. So we need to solve this using the constraint that is, let me write here, y plus c equal 1, x minus y plus 2, z equal 2. So perhaps we could, if you see what we need to do, okay, we need to take this x, y, z, relate with this. But I would like to do directly into the system. So what can I do? So the first one, I think easy to look at, it's as 1, 1, 1 constant, right? But we have here 2, 4, 6. So let's make them into the same constant. So I think the very best way is making them 12, right? The common factor. So make it 6 times, 3 times, 2 times, 4, 6. So we can make it 12. So let me write here to solve the linear equations. So 6, 3, 2. So this is what I think if you maybe having interest in this kind of problems, and you maybe you're also interested in algorithm and maybe coding. There are more sophisticated method in, I believe the course is called the linear algebra. Okay, if you are interested in, you could take a look on that as well. Okay. So first we could take this and adding all together. Okay. So this will be 12, 6,
x 12 x plus y plus z. Okay, yeah, 7 6 9 11, right? 11 lambda, and then 6 3 plus 4 7, right? So it gives, because this is 1, it gives value that is equal 12. Okay. Okay, and then the second one is a little bit tricky, so we need to do it one by one. You know, I think x, so we have to just divide by 2, y, and multiply with negative, and then divide by 4 to make it y, and then z divide by 3, and then adding the same particular method. This method is actually, we can correlate with the Gaussian matrix, but I think I will just do it manually. So 2x is x half lambda plus half mu minus y, so minus 1 over 4 plus 1 over 4 mu. It has a fraction, but I think the fraction will be, it will be disappear later. And then 2z is 3z divided by 2 half lambda, and then plus mu. Oh, y 3 should be 2, wrong. So 2z 1 over 3 lambda plus 2 over 3 mu. So this plus, so x minus y plus 2z (1 over 4, 1 over 3), it's 1 over 7. Yeah, it should be 7, because this is going to be very similar with the other part. So this is, but this is for lambda, not lambda, and this is for mu. So half, so 3 over 4 plus 2 over 3, 9, it's 11, right? And then the very same way, this will be 12, or I mean right here, this is equal to 2, right? This is equal to 2. And I will multiply with 12. So this will be 24, 7 lambda plus 11 mu. Okay, so we solve this too. So 7 lambda plus 11 mu equal 24. I think not really a good number, but we can try to solve, and multiply 7, multiply 11, right? Solving for mu, and then minus. Okay. So 7 by 7, 49. So 11, 77. So 49 mu. This is 84. Okay, it's 1 2 1. And then 24 and 11, what is 24 and 11? 264. Okay, not really good number. So this will be 8, 8, this would be 0, 8. Is my calculation correct? I'm also not really having confidence calculating this, but up until here is correct. Okay, so after we got this, but let me just check what is the final answer. Okay, what is the final answer? Let me check the correct answer. Okay, it says that the lambda is 6/23 and the mu is 30/23. Is it the same? Or maybe I have wrong calculation here. Let me just erase this part. Okay, I think you can just go there. And then substitute back to x, y, and z. So we are looking back to here. Okay. So substitute back. Okay. And then we get that x is 18/23. Y is -6/23, and z is 11/23. Okay, what can we do? Then lastly, just taking all this point into our functions. What is our function? This is f. So taking back to f x, y, z, and that is your value. Okay. So I'm skipping some process on here, just to find this elimination here, and then finding lambda and mu. Maybe I did something wrong. Okay, half. Okay, it should be 17. Oh yeah. That's why it seems that I got lost here. Okay, let me erase this. And this is 17. Okay, thank you. Okay, why I'm writing 11? Oh yeah. Okay, so yeah, and then check how to check the minimum or maximum. So suppose that you get the value from here. Okay? How to check whether it's maximum or minimum? You can check x, y, z that can satisfy the equation, and then you can check whether it is going to higher than this or below. Okay? If it is gotten higher than this, then this will be minimum. If that is going below, then this will be maximum. I think you can see from the constraint that we have x, y, z. Okay. So from these two constraints here, we could first take perhaps 0, 0, 0, but I think it's not satisfied because different values, right? So we could implore another point, and it suggests that you can try 0, 0, 1, okay? Or 1, 0, 0, or 0, 1, 0. But at the end of the day, this one is satisfying for both constraints. Okay. Because these two, it's I think very obvious that this will be equal, and then it should be 0, and this one should be 1, and I think that will be satisfied. It's going to be taking some trial and error, but I think for some points that easy to try, I think it's not really that taking much time to take that point. And then check the f, and you get that this is going to be equal to 3. Okay, which means that you need to decide whether this value is really significant to this one, okay? And how much different. Okay? If this is higher than the value that satisfied before, then this will be maximum. If this is lower, then this will be a minimum. We'll have a break. Okay, so we now move to the new chapter. Okay, the new chapter. So as maybe just a note that
After you get this point, check the value and then compare with your other value here. If this is lower, then this will be minimum. And I think if you check, this will be minimum, lower than 3. But if this is higher, then it will be maximum. So one of the, I think, the best feature of Lagrange, they can get you directly the extreme value, but you need to check whether they are maximum or minimum. You need to check.
Okay. Now we move to this part, which we call the multiple integrals. So, just a quick notes. Okay. In calculus 1, we get to define the integral. That is, if we have a curve like that, and we want to evaluate from A to B, then we define the integral as the area under the curve, right? So we define that the area under the curve is simply the definition by limit, and we take our approach to slice the area, right? Small pieces by pieces, and then adding all together, and that is what is integral, right? Okay. That is in the calculus 1. But now, in our multivariable calculus, we have something like this. Okay, for example, this is our surface. So we cut some pieces of it, and we define and project into our xy plane that we have some r here. Okay? So then we could select any points on this surface, and suppose that we are going to compute the volume. Okay, suppose that we are going to compute the volume, for example, maybe here. Okay, so we need to project it through the region below, and perhaps that is our R. Then simply, if we take this and we compute the volume, this is simply, if we have height and we have the area, then this is going to be area multiply, or you just write area multiply height. Okay, and I think just to see it in a brief or a glance, that the area, we could define the area through some small distance here and distance here. Okay, the area is it's from the x and y, which is the delta, small segment of x and y. So we could write the area as let's say the delta A. Okay, suppose a small segment of all the components, and then multiply with the height. The height is the function itself. So let's say we take a sample points, and then multiply with the f with certain coordinates at certain sample points, and simply, if we add all together all the volume, then we are going to do the same thing with our calculus 1, which is take the limit, but now we have a delta A. So what's to define the delta A? We could define it through the delta x and delta y. Okay, so we could define through 2, or let me write here, it's not really equal. This is going to be approximately, or no, right? Maybe just approximately first, and then write the limit later on in the definitions. So so first is x and maybe y here. So we have two sum that's going to define x and y, and then f. and we are going to have I and j to define the two axes, and then let's just write delta A for general. Okay. Okay, if you would like to see more clear, I think I will take this, and just to see that this R can be described in more clear observations through that. So we slicing all the segments become like a square or like a small rectangle. And then as usual, to find the total volume, we are going to add all the volume. So first we approach this one, a single one, and then we have another one here with different x and y, different coordinates as we see from the projection here, and we add all together. Okay? So we add all together by this notions of the sum, sigma notations. Okay, and then let me add here. Then if we take a look here, the smallest part, the smaller part it gets, the segments, we could see that it becomes more smooth. Okay, the graph becomes more smooth. Okay, so we make it more smaller, it becomes more smooth, as you can also predict from calculus 1. When you slice the graph, when you slice more and more sub-interval, it will become smooth. Okay, it becomes like an original graph, and this is also the same with the surface. This is a surface, and it becomes smooth. Okay, the roughness is decreasing, right? So we could take the first definition here, that double integral of a function f or fxy over rectangle R is equal And we could also define this integral in terms of volume, because basically what we did is compute the volume. So we could also write in another way. Right. Well, let me just go to the next page. I had all written, so it's more clear. So here. You could also write as if it is a volume. Okay? But basically they are similar. They are similar. They are going to approach the same volume. Okay, there are some approximation using Riemann and midpoint rule, but I will skip that. I will skip that because I think not necessarily needs for our case now. And what's important is how we are going to use this double integral. So suppose that we are going to define this. Okay? We are going to define this R. The R is going to be our region, okay? Region projected on X and Y. So let's say we have XY. Why it's not going over there? So dx dy, and let's say start from A, B, C, D. Okay. So how to read this? It means the inside integral will relate to this dx. Okay? So dx is going from A to B, and y from C to D. Okay? So the process, we try to integrate this. Okay, this is the first step to how to compute. Okay, and then this will be the second one. Maybe just a quick example. Okay, quick example. Let's say x squared y. Let's say we have dy dx. So we can switch dy dx here. Depends on the case. For example, we have the case this one, which means that dy here will be our first computation, first calculation. So we are going to integrate this x squared y just like our partial derivative. So we are going to take integration of y, okay, and just keep x squared as it is. Okay. So integrated. So first is here. So we integrate, and then we write half x squared y squared, and still the outside still have integral, okay, and still having dx. But the inside, we need to input the number that is going to be 1 and 2. So where to put the numbers? We need to put into the y. Okay. So put the number. So let's go that way. So 2 to y squared is 4. 4 minus 1 is 3. So it will be 3. Okay, so 3 over 2. So 3 over 2 x squared dx, and then we can integrate with respect to x. Okay, so this will be 1 over 3 x cubed, and this will be cancelled, so it will be 1 over 2 x cubed from 0 to 3. This will be equal to 27 over 2. Okay, this picture is to show you that how we define dA as dx dy. It's precisely we define here for x and for y. So this will be the distance that we are going to input in our area. Okay, now what if we switch the x and y? Okay, it will be the same integrations, but we are going to switch all y and x. Okay, so this will be 1, 2, 0, 3, same function, but now it's dx dy. Similarly, we are going to take the first step, the inside integrations. So we write 1, 2, we write with different color. This will be 1 over 3 x cubed y, and then 0, 3, and then dx. Okay, this will be 27 over 3 y, and then dx. Dy. And then integrated, then we have 27 over 3 multiplied by 2 and y squared. And then we need to take computation from 1 to 2. So we are going to cancel 3. So this is also equal to 27 over 2, which is the same result. This will lead us to one theorem which we call the Fubini theorem. Okay, they're on the left here. Okay. So it says that we can switch this x and y because they are the same thing. Okay. So if they are continuous, okay, and then we have some specific integrations, specific value that to compute, then we can switch this x and y. This is we call the this one here is we call the iterated integrals. Okay, we call this iterated integrals method, which translate that how to compute the double integral or the multiple integral. We compute from the first step, the inside integral, and then compute the outside. Okay. Okay. Now one more notes on this part is what we call the average value. And basically, it is quite similar to what we have in calculus 1. So in calculus 1, we have the average value. That is, we are going to divide with b minus a. b minus a is simply just saying that the distance. So just saying that the average value, if you have like a data, 10 data, okay, you're going to divide with the 10. Okay? But now, since we are in this function of two variables, we are going to divide with a. Okay? With 1 over a, which simply ends the first part of the chapter. Okay. So the first part is, I think, very short, not really long, but I think after 4 or 5, that will be a little bit longer. I think you just write the formula. Okay, just write the formula. The next sections, I will write the title first, which is the double integral over general regions. So what does it mean? Okay. So from the previous definition, we simply just limit within the rectangle, right? The rectangle R. But now we are going to have what we call this is called the general regions. So if the general regions simply in D, okay, or D is bounded regions, okay. So with this box, okay, we simply can have all the bounded regions D inside this R. Okay, so that's our first approach. Okay. So this means that if we take integral for D for such function, this will be equal to the capital F, which capital F is actually they are the same function but in D, dA, and we simply just change to R. Okay. Or simply, if we take the graph here,
that we can make in any regions, but simply we just take the box here and then we can define with the with these definitions. But what's more interesting is, I think the more you see the general regions, that this can be described as a function as well. For example, we have a function here that is y of x or f of x. We can simply draw a function here that could be an area that is bounded, and it is projected to the surface, and we can use this area as our segmentation for the integral. Okay. So basically, that is how we are going to look at. So we are going to at least having function of x in terms of y, or function of y in terms of x. It depends on this two. I think in your textbook it is defined as type 1 and type 2. But I think to simplify our understanding, there is no need to remember which type is it, as long as you know the relation between x and y. Okay. So let me just explain a little bit. Okay, I think we can move to here. Okay, so here we have projections from the regions, which we can see that I think we can get to function here. Okay? Function g2 of x and g1 of x. Okay? And then what we need is we are going to transcribe into our formulations. Okay. So how we are going to approach, okay, since you know the iterated integral as before, that is, so previously we have constant, right, all constant, but now, okay, since we have the function of x, so all here is function of x, okay, this is going to be function of x. So to write down this, which one is first, dy over dx, because this is actually y. Okay. So let me just write in more. So this is, we can write as y2, y1. Okay. So this is actually, we can write. So first we write as the original one. Okay. And then because we see that this is a function, not a constant, then that will be in the, we can write that inside. Okay, so this will be y, y1, y2. This is dy. Okay, so the outside will be dx because it's a constant. Okay, so all the functions that need to be written should be written inside, okay, because that should be compute first. Okay, I'm skipping some process here, but this is, I think, easy to understand logic for the double integral, and that's why you have this. Okay, so that's the very beginning. Okay, so we need to decide what kind of functions that appear within the subject here. Sometimes you can do both. Okay? You can relate the function in terms of function of x or function of y. Maybe one way or another. Maybe some. One way is maybe you get you prefer that way. It's okay, same. Okay? As long as you can relate the functions. Okay. So that in your book, this is called type 1. But do not really see the type, okay? But just to know how to relate the functions. And then if we have this, for example, this is for obvious reasons, this is going to be a function of y, right? Right and left. And this is, I think, the logic also similar to the calculus 1. Okay? If you have function of y, you start from the right, minus on the left. Okay? In function of x, start from the top, minus the bottom one, right? Okay.
Okay, and then the same way we get this, okay, for a function of y. But again, a function of x, function of y, it can be both. It can be both. You need to choose which one. Okay, and then how you describe the function. Okay, so the function will be inside, and the constant will be outside. Okay. So sometimes to solve problem within this subject for this double integral, sometimes you need to draw. You need to draw the functions. So you are given the functions. You're given the whole formula for the function of two variables. You are also given the region, and sometimes you need to draw regions. And for now, drawing the surface not really that necessary. Okay? Within this case, not really necessary. So you need just to know how is your function within this area, the region. Okay, I think we can go for several examples. Okay, let's start from here. And it's very obvious. Okay, this is the questions. Not yet the question. So evaluate d x plus 2y dA. Not really complicated. And d is region bounded by parabola y equal 2x squared and y equal 1 plus x squared, as we can see from the left side. Okay, sometimes maybe you are not, maybe the picture is not provided, but I think mostly the question will give you a very simple graph that you can draw. Okay. And simply drawing means just to let you know which one is on the top within this case. If you draw here, the top one is this one, right? 1 plus x squared, which means that this will be the one that on the top minus this, right? Okay. So in the integrations, that is on the top, and 2x squared is on the bottom. And then how to check the point for the constant, we can check the intersection. I think as we can see also, the intersection is already drawn, but let me just write the method just to be clear. So at x plus minus 1. Okay. So x from -1 to 1, right? That will be your integration for x. So first, the function will be defined as a function of x, which means y. So we could write down this is dy, dx. Dx is -1, 1. And dy will be from 2x squared and 1 plus x squared. And then we are going to integrate as usual. Start from here first, and then later we take the outer one. Okay. Okay, we simply write and then integrate with respect to dy. This will be xy plus y squared from 2x squared 1 plus x squared, and then this will be dx. And then input 1 plus x squared inside the y. So it has quite long now because we have two different components. So it should be x 1 plus x squared plus 1 plus x squared squared, okay, and then minus x 2x squared. Let me move a little bit to the left. And minus 2x squared squared. And then all, we need to take the integral one more time. So x plus x cubed plus 1 plus 2x squared plus x4 minus 2x cubed minus 2x4. Oh, this is not 2, sorry. It should be 4. So negative 4, negative 3. Still not yet. And then we take the integration. So yeah, quite a lot. And then take negative 1 to 1. Yeah, I think you can compute this, okay? I think this is from the textbook, I think. Let me check the textbook. This would be 32 over 15. Okay, I think one more question, or maybe two. Let me just write first question, find the volume of this solid lies under paraboloid Z and above D region. So D bounded. So D region is on XY plane. Bounded by that's the question, and that's the picture to help. Okay. So what's interesting on this part is, I think as we did previously, we can also take this 2x and x squared as our top and bottom equations. Okay, so that will be our dA, so our dy dx. But if we think clearly, okay, we can see this as top and bottom if we move this x. But also, we can also moving from the y part. If we move from here, we can also see that they are actually can be done, right? So we could also use
function of y. So it's up to you whether you are going to use 2x and x squared, okay? Or you could write in terms of x equal half y and x equal square root of y. For me personally, I will choose this one because I think square root sometimes made more complicated if you are not careful enough in your calculation. So, but that is possible. That is possible. So you could take x equal half y. Okay. So you can choose which one. Okay. In case you choose the just the original one, okay, just using the function of x, then this will be, let me write. This is a paraboloid. Okay. And then we can start taking the intersection first. Let me write the intersection. Intersection here, which is going to be 2x, x squared. So x squared minus 2x is 0. X minus 2 is 0. So x is 0. X is 2. Okay. Remember, do not ever cancel this. Okay. Okay. Really basic one. Okay, and then that is our constant. So let's use that here. And this is y, so y will be x squared to x squared plus y squared, and then dy dx. Okay. If you choose another way, then we need to check the constant on y. This will be 0 and this will be 4, right? And let me write with different colors. You could also write in terms of, so 0, 4, and then this will be half y and square root of y, x squared plus y squared. This is going to be dx dy. These two should result the same number at the end. It's the same. So you can choose which one, your method, okay, your path, left or right. I think I will give this to you to solve it. Let me check whether we have, I think the other also similar. Okay. Remember the Fubini theorem as we mentioned previously? Now because we have a function here, the further question is, can we exchange this becomes dx dy? The short answer is yes, but how? That will be, I think, tomorrow's lecture. Okay. I think I will end up until here. Yeah, just end up to here. You can try to solve this and maybe perhaps remembering some techniques in integral in calculus 1 also.